Hi, everybody. Thanks for joining us for Phosphorus Science Now. I'm the host, Matt Scholz, and the program manager for the Sustainable Phosphorus Alliance. And I'm joined today by our guest, Dr. Katrina Macintosh. Katrina is a research fellow in the School of Biological Sciences at Queen's University Belfast in Ireland, and she works on phosphorus sustainability and water quality. She's also a program manager for the Irish Nutrient Sustainability platform, which was funded via an Environmental Protection Agency of Ireland grant. And Katrina has written with her colleagues a very interesting paper that was recently published in Science of the Total Environment. The title of the paper is Transforming Soil Phosphorus Fertility Management Strategies to Support the Delivery of Multiple Ecosystem Services from Agricultural Systems. Katrina, what was the context for writing this paper? Why did you decide to do it? And what's sort of the landscape of other articles and other research that's going on that made this an important contribution?
The background to the production of the paper was through meetings of the Phosphorus Research Coordination Network, where co-authors came together from varying backgrounds to look at how we might transform current soil fertility management strategies to basically support the delivery of multiple ecosystem services within agricultural systems, particularly that agricultural production is driven currently by economics and the demand to deliver on maximum potential yield and therefore profit. And sometimes this is often to the detriment of the environment and impacts negatively on other ecosystem services. So we selected 4 key metrics looking at crop yield as a key ecosystem service, and also then P retention, looking at how soil retains P as a proxy for water quality, also looking at biodiversity and carbon sequestration and how those 4 example metrics can be balanced relative to soil test phosphorus to deliver on the ecosystem services, and look at how that can be incorporated into current management strategies, such as the 4R strategy or the 5R approach to sustainable phosphorus management.
So Katrina, you talk in this paper a lot about ecosystem services, and I was wondering if you could give us some examples about what ecosystem services you're talking about.
Sure, Matt. Ecosystem services are the benefits people obtain from ecosystems. These include provisioning services such as food, fibre and fresh water, regulating services like climate, flood and disease control, cultural services, including spiritual and recreational benefits, and supporting services such as nutrient cycling, soil formation, and biomass production.
Yeah, I was wondering if we could walk through a couple of the figures in the paper. So if we could start here with your first figure, could you explain a little bit about what this figure is telling us and what it says about the trade-offs between ecosystem services?
Sure. In this paper, we basically explored the relationship between soil test P and the delivery of 4 key ecosystem service metrics, namely crop yield as an ecosystem service, phosphorus retention as a proxy for water quality, biodiversity and carbon sequestration as indicators of ecosystem services. And what we see on screen is a conceptual model for advancing soil P fertility management based on the delivery of those ecosystem services or indicators of ecosystem service, where we're able to provide an economic value to the ecosystem service or indicator as influenced by soil test P concentration. So agricultural production is driven by economics and the demand to deliver maximum potential yield. And this is often to the detriment of the environment, which has negative impacts on ecosystem services. In our conceptual model, we can see that as soil test P concentration increases, depicted on the x-axis, the ability of a soil to retain P decreases, as we can see with the red line. This has negative consequences for water quality. The same can also be said for species diversity and carbon sequestration, which also decline at different rates with soil test P increasing. To manage the delivery of multiple ecosystem services, we argue that soil test P concentration offers a common unit of measure by which ecosystem services can be economically valued relative to maximum potential profit in terms of dollars per hectare per year. For example, we can see that in this model, there's no increase in yield is achieved above 20 milligrams per kilogram of soil test P, and the yield line plateaus out. Whereas below 20 milligrams per kilogram of soil test P, yield declines, but P retention in the soil increases exponentially. Therefore, the economic value of maintaining the soil test P levels below the in terms of lower yield can be estimated and then traded or offset against delivering on water quality objectives. The same can then be said, and other objectives can be set for carbon sequestration and species diversity.
Okay, great. So this provides sort of a conceptual model for the paper, and these are hypothetical data in Figure 1, correct?
Correct.
And then in Figure 2, you actually modeled some actual data from New Zealand. Is that correct?
Yes, in Figure 2, we can see the relationship between soil test P and crop yield is usually described by a rapid increase in yield with modest increases in soil test P concentration, followed by a plateau in yield as soil test P concentrations further increase. This is illustrated in the example from New Zealand shown on screen, which showed pasture yield production in the orange dots, the potential for P loss as red dots, and as well as plant species richness illustrated as percentage clover, and carbon sequestration as a percentage carbon as a function of soil test P measured as Olsen P. Again, trade-offs can be made in relation to grass yield based on targets for water quality, carbon sequestration, species richness relative to soil test P level.
Okay, great. And so just so I'm clear, on this graph, the red dots are increasing, and that's because this is measuring soil P loss, whereas in the hypothetical model, we're looking at soil P retention, and that's why it was declining, correct?
Yes.
Yeah, great. You feel that the data that you're seeing here supports the model that you had developed originally?
Absolutely. It's showing as soil test P increases up to a certain point, you get increasing yield. Beyond that, you're not getting an increase in yield, but you are beginning to see increase in soil phosphorus losses from pasture, as well as balancing the percentage clover and percentage carbon. So you're able to trade off the different ecosystem services based on the targets that you wish to achieve.
Okay, great. And then we can move on to the third figure in the paper. So here you're talking about some data, not in New Zealand, but here in the United Kingdom. Can you tell us a little bit about what you're accomplishing here?
Certainly. The typical soil P fertility advice is advocating for a critical soil test P concentration that translates to 95 to 98% of relative maximum yield, and this is known as the agronomic optimum. However, soil test P concentrations do not always accurately predict the adequacy of soil P supply for optimum yield, if factors such as soil type, soil pH, and buffering capacity and other supply of nutrients are not taken into consideration. In this example shown in Figure 3, we can see that actually for more than half of the UK study sites, as reported by Johnson and Morrison, actually require less than the recommended agronomic soil test P concentration for optimum wheat and barley yield. Therefore, site-specific factors must be taken into account when guiding soil test P levels. And as we can see, across the Olsen P gradient, the variation in yield is not massive, so you can adjust or reduce Olsen P without massive implications on yield.
And then in the fourth figure of the paper, you talk about how increasing soil test P and specifically Olsen P correlates with increases in dissolved reactive P. Again, you're working in New Zealand in these sites. Can you talk a little bit about that?
Certainly. As we can see from this figure, the potential for P loss from land to fresh water increases linearly or exponentially with increasing soil test P concentration measured as Olsen P. This figure 4 illustrates the variation that exists in the relationship between Olsen P and dissolved reactive P for 6 sites in New Zealand, ranging from low to high soil P absorption capacity. And the absorption capacity of the soil has a strong controlling effect on the quantities of dissolved reactive P. And the relationship between soil P and P loss is a function of the soil's ability to retain phosphorus and is determined by its geochemical, biological and hydrological characteristics. And this is very important in terms of soil fertility management recommendations.
Yeah, and so that leads to the question, do we need to change how we measure soil test phosphorus in order to accommodate better ecosystem services valuations? And if so, is that practical for farmers and other folks to do?
Yeah, we could change current soil test P regimes because the majority of current management decisions are largely based on agricultural production in terms of yield. We now advocate the need to move away and incorporate and balance other ecosystem services and move away from insurance level applications of phosphorus towards more precise soil P fertility management to deliver on, for example, water quality and biodiversity. In Table 1 in our paper, it details the barriers and actions needed to implement an economic optimum approach that delivers and optimizes ecosystem service delivery.
You would actually advocate then, what tests how would you change the test exactly?
Changes can be made to improve existing soil tests or try and develop new tests that are calibrated for ecosystem services, including P buffering capacity and turnover. We can also look at trying to incorporate site-specific conditions and also then change from agronomic to economic approach in terms of moving away from current insurance-based fertilizer applications and also consider temporal variability, alternative sources of fertilizer and fertilizer placement and timing, and develop decision support systems to basically accommodate real-time information on soil and crop nutrient supply.
If we don't maximize yield, then to meet the demand for that crop, some other land is going to have to be put into production, correct? And if that's true, then and we have a very global economy, you don't necessarily know where that land is going to be. So is it difficult then to model the trade-offs between the sacrifice you've made in yield and the benefits you've obtained through protecting those ecosystem services, in sort of disjointed locations?
Absolutely, and a key step in terms of policy adoption is to produce and collate data sets and case study examples that demonstrate the conceptual curves we have in our paper over a wide range of conditions in farming enterprises, and also need to consider then how such an approach could be incorporated into existing frameworks for payments for ecosystem services. And this is an area warranting further consideration. But yes, the trade-offs between reducing yield for delivery of other ecosystem services and then bringing in more agricultural land into production is basically a difficult question. In the first instance, I suppose we can strive to make soil test P recommendations more accurate to soil and crop requirements, and thus reducing the potential for losses to water, therefore making and improving on water quality. At the catchment to national scale, we need to consider productive capacity of land and the environmental constraints to be worked within. And this, for example, will indicate where sustainable productivity can take place, depending on the environment and the land suitability. Other trade-offs also might include, future new innovative farming systems and changing consumer food choices to prevent more land being brought into production.
Okay, great. Thank you, Katrina. So do you have any other concluding points you'd like to make about this paper before we close out?
A couple other concluding comments really is we do recognise that soil P fertility is only one of the contributing factor to ecosystem service delivery. However, we do recognise that effective nutrient management is integral to the success of sort of strategies and sustainable farming. And we highlight that there's currently no operational framework in place to manage P fertility for the delivery of multiple ecosystem services, and a mechanism to identify costs of potentially sacrificing on crop yield and profit for the delivery of ecosystem services. So the conceptual model and the examples we illustrate help to support the use of an economic approach to P fertility and how we can then assess and trade delivery of one service against another using standard units of dollars per hectare per year.
Well, great, Katrina. Thanks so much for joining us today. It's been a very interesting discussion, and you've provided an interesting framework. And thank you all for joining to listen in on Phosphorus Science Now.